All right, so we are in unit number 1. Today we're going to talk a little bit about viscosity, which is related to our discussion on matter, the properties of matter. And today we have our lab, so we're going to learn some lab skills. So we're going to design an experiment based on a hypothesis. We're going to get some data from that experiment, so we're going to analyze it by graphing it. And from there, we should be able to really understand the relationship between viscosity and temperature. And again, we're going to do the 1C lab, and your goal should always be to get an 80% or higher, right? Because we want really we want to really understand the content, as well as 80% or higher means B's or better. Okay? So really quick review from yesterday. Remember, physical properties don't change, or physical changes don't change the chemical makeup of matter, right? Remind me again, right? Think about ice versus steam versus liquid water. They are all still molecularly what? What chemical are all three of those things still? Even though they're changing their phases, changing their state. Yes, I see Efren's got it. In the chat box, we should all be participating. It's okay if someone else says the same answer as you. It helps to reinforce your own learning, though, to still type it in. All right, so reinforce your own learning. All right. Awesome. Yes, H2O, right? So all of those things are still H2O, even though it's changing kind of what form it's in. It's still H2O though, so we haven't created any new substances. So the smell of something can change. You can freeze it, you can boil it, you can melt it. Its viscosity can change, its density can change, and it's still not going to change the substance's chemical identity. So those are only physical changes. Smiley faces if we understand. Confusion faces if we are confused. I know there's many different ways to participate, Efren, and many people are participating through like emoticons and stuff like that. So it's okay. Through emojis. All right, now chemical changes can change the chemical makeup of matter, right? So for example, hydrogen and oxygen, when they are together and you ignite them and they explode, they will actually create water, right? So that creates a different type of substance, a different chemical. Same thing with zinc reacting with hydrochloric acid. This releases hydrogen gas, which is a different type of chemical. The ending chemicals are different. Same thing with acids and bases, like acetic acid and vinegar reacting with baking soda. All right, when those two things react, they neutralize each other, creating something different. They create water and salt. All right, so we are creating different things with chemical changes. All right. So that being said, one of those things I mentioned was viscosity. And viscosity is kind of how thick a fluid is. All right, so viscosity, the definition is it's a fluid's resistance to flow, meaning resisting flow means how difficult it is to move, okay? So if something is more viscous, all right, it's going to be thicker, it's going to flow more slowly, it's going to be harder to move. So think about it in the chat box, what's more viscous, honey or water? What do you think? What's more viscous, honey or water? Yeah, honey is much more viscous. It's got a high viscosity, it's thicker, it flows much more slowly, right? If you think about pouring out honey, it takes forever. I actually have honey on my sandwich right now, and I was making it before class began because I procrastinated on some stuff, and I was like, flow faster, honey, right? So honey takes a long time to move. Water, on the other hand, has low viscosity, right? Water's much thinner, and it flows much more quickly, okay? So again, this is all physical changes though. So we can actually make honey change its speed, change its viscosity without it changing from honey. It's still actually honey. Same thing with water, right? Solid water is it's gonna not move very quickly as opposed to liquid water, right? So we can actually change these things without changing their identity. Okay, that's why it's a physical property. All right, this is number 1 in your ticket. Please give me a green check when you have the blank filled out with the word resistance. The first blank in number 1, or the only blank in number 1, should be filled out with the word resistance. Green checks, everyone. All right, Amir, Andrea, Brianna, Bree, Chanel, Donnie, Dorian, Dree, Dylan, Ireland, Israel, Jake, Jasmine, Jody, Joe, Cash, Kyler, Letty. Green checks, please, everyone. Michelle, Miguel, Oscar, Stacy. Okay, green checks for number 1. We're going to move on in 5 seconds. We go. All right, so here's what our lab is going to go over today. It's going to take a look at how temperature influences viscosity, how temperature and viscosity are related, temperature and the thickness of a fluid, okay? So we're going to follow what's called the scientific method. Go ahead, give me a thumbs up if you have seen this before. All of you that have had me before should have definitely seen this, but I know we do have some new students this quarter. Okay, so the scientific method is just the way in which we investigate the world around us. And it doesn't always follow these exact steps. It looks different based on what you're investigating, but this is a good general outline. Okay, so when we are trying to figure out what's going on in the scientific world, the first thing you need to do is make observations. Look at what's happening around you, figure out what do you observe. From there, we're going to ask a question. Why is something the way that it is, or how does it work? From there, we form a hypothesis, which is an educated guess or a possible answer to our question, right? So we have a question and we think maybe this is the answer, our hypothesis. That helps us to perform an experiment so we can test our hypothesis, and then we get a bunch of data from that experiment. From there, we can analyze that data using things like graphs, and that allows us to draw a conclusion of whether or not our hypothesis, our guess, was correct. All right, if we support it, then our guess is correct, our hypothesis is supported, versus if we disprove our hypothesis. In that case, we might need to go back and change our hypothesis to a different one so that we can try it again, right? Smiley faces, everyone, if that makes sense. Smiley faces if you understand that process. All right, and we're going to actually kind of go through this process today, so you'll become more familiar with it if you're not already. Okay, so that being said, really quickly, what are the 5 senses that are used to make observations? I've got some hints here for you. Those of you that have had me before, you know the drill. What are the 5 senses? No worries, Oscar. Yes, we've got sight. What else do we have? Yes, we've got smell. Oops, that's not smell. Nobody smells with their ears. Yeah, we've got hearing. What's this one? Yes, this one is taste. And last but not least, we have, yes, touch. Awesome. So we can use these 5 different senses to observe the world around us. We can also use scientific instruments and then take our observations from those instruments. All right, so what we're going to do is I'm going to go ahead and show you a video, and during the video you're going to make some observations. Obviously, you're not going to use all of your senses. Please don't start licking your computer to try to taste the video. All right, but we are going to go ahead and use some of our senses to make some observations. All right, so here we go. Oops, that's not what it, sorry. Sorry, I'm going to go ahead and find it again. Don't taste the computer. You can use your past experiences. There are definitely some of these things that you've actually done before. All right, so where did it go? Hold on. Huh, that's weird. Okay, hold on, guys. All right, I'm going to just share it through YouTube. All right, here we go. I'm going to go ahead, put it up on the whiteboard, and then I'll also put it in the chat box if you need it there. All right, here we go, in the chat box and on the whiteboard. Start watching. Green checks when you finish.
Hey, hey, hey. Welcome to my live chat. Let's start with some questions. Ooh, gold map.
I'm taking this month off, and while I'm gone, 5 other YouTube creators have lined up some brilliant guest videos for you. We start with science presenter Steve Mould, and when he told me the title of this video, I thought, no, I can't. And then I was wrong. So, be nice, be kind. Steve, take it away.
You have a superpower that you're probably not aware of. The ability to hear temperature, or at least the ability to discern between hot and cold water just using your sense of hearing. And this is something we can test. So I'm going to pour hot and cold water from these identical jugs into these identical mugs. And it's your job to figure out which is which. And I'm going to blur the screen as well because there may be some visual cues that would tip you off one way or the other. Okay, here we go. It should have been quite easy to tell which was which. Feel free to pause the video and leave a comment with your guess if you like, but here's the answer. The first pour was cold and the second pour was hot. And the reason they sound different is because of the fact that water is viscous, or thick, if you like. And the viscosity of water goes down when you heat it. This is something that's easier to see with a liquid like honey. So warm honey is more runny than cold honey. Whereas with water, it's less visually apparent. But when you pour water, the way it splashes into a cup is affected by the viscosity. And this change in the splashing of the water changes the sound that it makes because of various complex fluid dynamic reasons. What's really interesting is this is knowledge you already had due to a lifetime of hearing cold drinks and hot drinks being made. And like many things, this is something that you knew intuitively, even though it wasn't something you were aware of consciously.
Go subscribe to Steve Mould's channel. I would recommend his...
All right, everyone, green checks if you finished watching it. If it's not loading right away, you can watch it a little bit later. I sent that link to you. Awesome. All right, so who guessed correctly? Who guessed correctly? Tell me in the chat box. Yeah, awesome. And what did you guess? What was the result? In terms of the one that had a higher pitch, the first one, what was that one? Was that one the cold one or the hot one? The one with the higher pitch. I know, it's super surprising, isn't it? Yeah, the cold one. So the cold one had a higher pitch, right? It had a higher kind of noise, whereas the hot one had a lower pitch, right? It sounded kind of softer, right? Smiley faces if that makes sense to all of you, right? So cold had a higher pitch that was sharper, right? Hot had a lower pitch that was softer. Yeah, no problem, Masail. I'll send it again. Here you go. Yeah, exactly. So the thing is that cold water, just like cold honey, is actually more viscous. Even though we can't necessarily see it, we can hear it, right? So we can actually hear that cold water kind of hits the cup a little bit harder because of it's actually slightly thicker, right? It's slightly more viscous, right? So let's go ahead again. Our question for today: what two things are we trying to relate to each other? Tell me in the chat box. What two things are we trying to relate to each other in this lab? Yeah, you have lots of amazing powers. Tell me in the chat box. What two things are we trying to relate today? Let's think back to our mind map, right? What two things are we taking a look at today? Go ahead, tell me in the chat box. Awesome. I see Arrow typing. I see Caleb typing. Everybody should be typing. Everybody should be participating. There we go. Thank you, Efren, Ireland. Let's go. Yeah, what two things are we trying to see are related to each other today? There's two vocab words that I'm interested in here. No worries, Caleb. Yeah, just stay with us for the rest of class, and anything you missed will be in the recording. Yeah, we're taking a look at temperature and viscosity, right? We want to see how temperature, right? How temperature affects viscosity, or the thickness of a fluid. Awesome. All right, so here's where we're going. We've got our observation: when a fluid like water or honey is heated, it becomes runnier, right? It becomes less viscous. And we want to know, how does temperature of honey influence its viscosity? So we should already know probably what the result is going to be. So this is our hypothesis because we probably know that this is going to be the answer. So if honey is hotter, what do you think is going to happen to its viscosity, its thickness? Do we have more viscosity, more thickness, or less viscosity, runnier? What do you think? Hotter, 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 hotter. Yes, we're going to have less viscosity. So then less viscosity, making it runnier. Exactly. Okay, what about it's gonna be runnier, it's gonna flow faster, right? Runnier and flow faster. Awesome. Now, if honey is colder, what happens? Tell me in the chat box, right? We can say it the opposite way as well. If honey is colder, then what happens? Go ahead, synthesize that together in the chat box. Yeah, it's going to get thicker, right? It's going to be more viscosity, right? Because it's going to be thicker and it's going to flow more slowly. Excellent. All right, so that's where our hypothesis is today. Okay, so here's what's going to happen. I'm going to go ahead and send you the links to your lab right now. All right, so you're going to go ahead and open up your lab report. Now, if for some reason your computer does not allow you to have more than one tab open during class, Dolly, it's in your lab. It's already written in your lab. All right, so I'll show you that in a moment. All right, but if for some reason your computer really hates having Blackboard and multiple tabs open, it's okay. All right, you're not going to miss anything. You don't have to have it open. I just recommend taking pictures of what we go over in class today. Okay, smiley faces if that makes sense. I'll give you a little bit of time to work on some of the questions, but again, if you're a slow typer or if you can't have your lab open for some reason, just take a picture. Use your phone, take a picture. Okay, cool. All right, here we go. So our hypothesis, you see this in question number 1 of your lab. Our hypothesis is if the temperature of honey is hotter, then it's going to have a lower viscosity, aka otherwise known as, it will be runnier. Or you could say it the reverse, if the temperature of honey is colder, yep, here it is again, Efren. Here's the lab. If the temperature of honey is colder, it's going to have a higher viscosity. It's going to be thicker. Okay, so take a look at this. We have 2 things that we need to figure out here. We need to figure out what is the independent variable of our lab, which means what is the thing that we're changing on purpose at the start to our honey. Tell me in the chat box, what are we changing on purpose to our honey? Take a look at the first part of our hypotheses. Take a look at the first part. All right, I just underlined them. What are we changing on purpose about our honey? Yeah, we're changing the heat or the temperature, right? So we're going to change the temperature of the honey, all right? And today we're going to be measuring that in degrees Celsius. Oops, degrees C, not degrees C0, Celsius. Cool. Now our dependent variable is going to be what? What is our dependent variable going to be? Take a look at the second part of our hypothesis, the end of our hypothesis, the then parts. Then it will have what? Go ahead, tell me in the chat box. What was the other vocab word that we talked about today, right? We said temperature related to what? What's the result that we are measuring today? What are we looking at the end for our honey? Awesome. Again, if even someone else says the same answer, you should still type it in just to reinforce your own learning. Yeah, exactly. So this is going to be viscosity. Exactly. So viscosity, which in this case, we're going to be measuring the distance honey travels in 30 seconds, okay? And the reason for this, the reason that we're measuring it this way is because, again, if it's less viscous, it's going to go further in 30 seconds because it's thinner, runnier. If it's more viscous, it's going to not go as far because it's much thicker and less, and it moves much more slowly. Smiley faces if that makes sense. So that's how this lab is going to measure that today, okay? This is the answer, yes, so this is now your answer to number 1. So take these 2 things and these should help you answer number 1 in your lab. Give me a green check when you have these written as your answers to number 1. You can copy these. That's fine because that's the actual answer. Please do not type the actual definitions of independent and dependent variable. Those are not the answer. You need what I have circled here. Green checks when you have those saved or you've taken a picture. Go, go, go. Waiting on a green check from Amir, Tony, Bree, Chanel, Dolly, Donnie, Dree, Dylan, Edwin, Ireland, Jake, Jade, Jackie, Jasmine, Joe, Kyler, Letty, Michaela, Miguel, Blossom, Razi, Suji, Whitney, Yolese. I don't know what you just said in the chat box, Efren. Sorry, there are a couple spelling errors there and I don't know what you just said. Cool. All right, guys, let's go ahead and keep on going. All right, so this is going to actually be a video lab that the people that K-12 has already actually created for you. It's okay, Jade. It will be in the recording. Yeah, I have a class directly after this, so I can't stay after class, but the recording will be uploaded at 2 o'clock. So just make sure you have the password saved for today. Okay? So can we, but for cause... and effect. I don't know what you're saying, Efren.
Hi, I'm Pat Keeney, an instructional designer with K-12. Along with my assistant, we're here to work with you on a lab that explores the viscosity of honey. In most lab work, advanced preparation is needed and safety is always important to consider. Viscosity is a fluid's resistance to flow, while substances, such as honey, are described as being viscous. All fluids can be characterized by their viscosity. Molasses, motor oil, and honey all have high viscosity. Water, juice, and rubbing alcohol all have low viscosity. In this lab, you will see how viscosity responds to temperature. The important question to consider in this lab is, How does viscosity change with temperature? Viscosity indicates the thickness of a fluid. Specifically, viscosity is a fluid's resistance to flow. In this experiment, we will warm up cold honey and then measure how it flows down a ramp to demonstrate how temperature and viscosity are related. Use your observations and prior knowledge to write a hypothesis that describes how viscosity changes when temperature changes. A good hypothesis should take the form of an if-then statement, such as, if the temperature increases, then, well, you finish the rest. Honey packets can be made in advance by putting 1 tablespoon of honey in 7 snack-size, zipper-closed plastic bags. Or you may obtain honey packets in a cafeteria or restaurant. Freeze the honey packets for several hours. We made a tray of ice cubes, which was needed to lower water temperature during the experiment. Before beginning the lab, we will create a data table with the following columns: temperature in degrees Celsius and distance covered in 30 seconds, measured in centimeters. We'll get our ramp ready by placing aluminum foil under one end of a cookie sheet to catch any spills. First, we tape a metric ruler to a cookie sheet lengthwise, with the 30-centimeter end near the bottom of the sheet. Then we add a piece of tape to create an easily visible reference point as a starting line. Now we're ready to get started. We put a thermometer in a large plastic container and then filled the container with water that was about 70 degrees Celsius, slightly colder than what is needed for hot tea. We then recorded the water temperature in the data table. We were concerned about some safety issues. For instance, if the water is too hot, it would melt the plastic honey packets. Never microwave honey packets. They will heat up extremely fast and the microwaves weaken the plastic. The packets may break when you handle them. Hot honey can cause bad burns because it sticks to your skin. To warm the honey, we placed a honey packet in the water for 5 minutes and then removed the packet. To get the best lab results, we sealed the packet securely before placing it in the water and dried the packet when we removed it from the water. This avoids mixing any water with the honey. Water may alter the viscosity of the honey and therefore could compromise the experiment. Next, we removed the packet from the water, dried it, and then used scissors to snip off the corner of the packet. With the cookie sheet flat on the work surface, honey was squeezed onto the sheet near the 0-centimeter end of the ruler. We lifted one end of the cookie sheet off the table and onto the container so that it was angled, allowing the honey to flow down the sheet toward the 30-centimeter end of the ruler. To get the best lab results, understand that certain things may vary, such as the honey itself, the indoor temperature, or even the type of cookie sheet. In the first trial, if the honey moves too fast or too slowly, we could increase or decrease the time of the trial, or tilt the cookie sheet more or less. After the first trial, we have to be sure to always use the same setup for each succeeding trial. Notice that we were certain to wipe all the honey from the cookie sheet. We repeated the entire procedure using water at approximately 40 degrees Celsius to warm the honey. Then again using room temperature water at about 20 degrees Celsius and in ice-cold water at approximately 0 degrees Celsius. We used ice to lower the temperature of the water. You probably understood before beginning this lab how viscosity is related to temperature. Now that you have seen this lab conducted, you should be able to describe that relationship. You will be provided with data from this experiment and possibly others like it. In all cases, the same procedure has been used.
Okay. All right, guys. So here we go. I'm going to go ahead and I'm going to send you the link to how they did the experiment. I want you to watch this link because that's going to help you understand how they did the experiment, okay? Awesome. All right, so here we go. You have actually been given the data already. So what you're going to be doing is after you watch the video, you're going to use the data that they provided you in order to graph and analyze the data, okay? So here's the data that they gave you. You'll also see this in your actual lab, okay? So I'm going to go ahead and show you exactly what this looks like. The first thing is that you do need to have a Google account in order to do this, all right? Smiley faces if you already have a Google account, all right? Many of you should because you had me as a student last quarter, okay? If you don't have a Google account, it's very easy. All you need to do is go to accounts.google.com/sign up. And you want to make sure that you save your username and your password because we do use the Google account every time we need to graph something, okay? Now I'm going to go ahead and show you the instructions. Please just watch them. Don't try to do it on your own right now because if you lose your spot and you get distracted, I can't go back to something that you missed. So just pay attention, just watch what we are doing. All right, so I'm going to go ahead and show this to you right now. Smiley faces if you understand. You're just watching the instructions. You're not doing anything yet. Just watch. Cool. All right, here we go. I'm going to share this with you. Awesome, awesome. All right, so let's take a look at this. So we've already done question number 1 together. Again, you should have filled out what our independent variable was at this bullet point, the dependent variable at this one. Do not write the definition. I don't want the definition. I want what they actually are in the experiment. Okay? From here, what you are going to do is you are going to click where it says Viscosity Data in Graph Google Sheets Template. Okay? Now, again, you do need to have a Google account. You need to already be logged in order for this to work. Okay, so you're going to click on this, and when you click on it, it's going to ask you if you want to make a copy, and you're going to click Make a Copy. Okay, so you'll make a copy. And from here, you have your template of where you're going to enter your data, and you actually will also have a graph right here that will update as you enter your data. You don't need to do anything to the graph. The graph is already set up to update when you enter your data. Okay, so we're going to copy the data from over here, okay, exactly as you see it. You are supposed to use this data. You should copy this data. You don't have to do the lab at home on your own. Okay, so for example, the first point is at 70 degrees. We cover 7.2 centimeters in 30 seconds. So up here, I would write, up here, I would write 70.0. And then over here, the distance again was 7.2 centimeters. Now, really important, please only type numbers into the colored boxes. You don't need to put degrees Celsius, you don't need to put centimeters because those are already included in the titles. Okay, so don't put any letters in here. If you put letters in here, your graph will not show up correctly. Thumbs up if you understand. Thumbs up if you understand. Okay, don't put letters in here, only numbers. Okay, perfect. Now, that being said, you would then enter your next point, which for here is going to be 46.1, right? So 40 degrees, it moved 6.1. Remember to always press enter or click out of the box. A lot of you always have a single point missing just because you forget to click out of the box. It will not save unless you click out of the box. All right, so click out of the last box so that it saves. Okay, and you'll see that it begins to update here automatically. All right, it's already updating for you. So you'll fill out the rest of these, right? So this 25.3 should go in this green line. 4.7 should go into the blue line, and 4.4 should go into the pink line. I'm not going to do that because I want you to actually do it yourself. I want you to actually do that work yourself. Okay, cool. So once we have this, all right, all we need to do is get the shareable link. The shareable link is what you're going to give here, and that's how you're going to turn in your graph in your data. That's all you need to do here. So in order to do that, all you need to do is click share, click get shareable link, click copy link, and then you just need to paste it into the answer box. Those instructions are right here for you as well. Smiley faces if that makes sense. So you can right click and paste. You could also press Control V if you're on a PC, or you can press Command V if you are on a Mac. That will allow you to paste it in there. Okay, so that's all you have to do for question number 2. Super simple. Yep, so you type exactly this data here, these numbers here, into the table in our template here. Okay, awesome. Now, question number 3 asks you, do your results support or disprove your hypothesis? Okay, in these little red blanks, you're going to fill in the correct words. All right, and those correct words, I give you those options right here in yellow. Okay, so very easy. You're going to go ahead and fill out your conclusion based on what you see here. Okay, and then question number 4, you're going to go ahead and use your trend line to predict how far you think honey would flow at 80 degrees Celsius. To do this, all you need to do, you might want to zoom in on this. Okay, you're going to go down to where you see 80 degrees Celsius on the bottom here. Take a look at your trend line right here, and then figure out where does that trend line intersect the distance covered. So right here, just go all the way to the left at distance covered, which for me it's about 7.6 right now, but it obviously will probably change as you enter more data in. Okay, so I would, for example, say 7.6 centimeters, but obviously yours will probably change, so don't copy that. Okay, sound good? That's easy peasy. That's all you need to do, and then you would submit your lab, and your lab is worth 100 points. All right, so smiley faces, everyone, if that makes sense. All right. Yes, Efren, what's your question? Dree, I would type them. Don't just copy paste. If you copy paste, you might mess up the formatting. Okay, cool. All right, everyone. So again, you figure out, does your data support your hypothesis? Fill that in for question number 3. Yes, just enter the numbers. Exactly, Efren. And question number 4, again, is using that trend line. And again, this is in the recording, so if you miss anything, it's in the recording. Okay? All right, guys, so here was our objective: experiment, hypothesis, graphing and analyzing viscosity and temperature.